Become a sustaining member of the Commonwealth Club for just $10 a month. Join today.
Hello and good afternoon. I am Patty James of the Commonwealth Club's Health and Medicine Forum. It's my pleasure to extend a special welcome to any new club members who are here for this digital program. I encourage our viewers to become members of the Commonwealth Club. To learn more about membership and its benefits, please visit the club at www.commonwealthclub.org. To support the club right now with a tax-deductible gift, please click the blue donate button on your screen. One quick note before I introduce today's guest. If you have a question for our guest, please post it in the YouTube chat area. Those questions will be forwarded to me. And now it is my great pleasure to introduce Dr. David Ludwig. Dr. Ludwig, MD, PhD, is an endocrinologist and researcher at Boston Children's Hospital, professor of pediatrics at Harvard Medical School, and professor of nutrition at Harvard School of Public Health. For more than 25 years, Dr. Ludwig has studied the effects of dietary composition on metabolism, body weight, and risk for chronic disease, with a special focus on low glycemic index, low carbohydrate, and ketogenic diets. Described as an obesity warrior by Time magazine, Dr. Ludwig has fought for fundamental policy changes to improve the food environment. He has authored more than 200 scientific articles and presently serves as an editor at the American Journal of Clinical Nutrition and the BMJ. Dr. Ludwig is author of the #1 New York Times bestseller, Always Hungry, available for purchase from the Commonwealth Club today. Conquer Cravings, Retrain Your Fat Cells, and Lose Weight Permanently. Dr. Ludwig will be discussing his latest study today, the carbohydrate insulin model, a physiological perspective on the obesity pandemic, through the American Journal of Clinical Nutrition. And the link to the study will be available to you. Thank you for being here with us today, Dr. Ludwig.
Thank you, Patty. It's a great honor and pleasure to be with the Commonwealth Club. We can see them?
Mm-hmm. Yes, we can.
A famous law of physics, first proposed by the German Rudolf Clausius in the mid-1800s, says that energy can neither be created nor destroyed. Applied to body weight gives the familiar equation calorie intake minus calorie expenditure equals calories stored, mostly as body fat. That's our main storage organ for excess calories. According to the conventional view, obesity is a failure to control energy balance. Living in our modern food environment surrounded by energy-dense, tasty foods, it's easy to overconsume, and we don't have much opportunity to burn off those calories with our sedentary lifestyle. They build up as calorie-rich fuels in the bloodstream and get forced into fat cells, making them anabolic or making them grow, and we gain weight. This energy balance model has two key features. First, all calories are alike to the body. And second, to lose weight, you have to eat less and move more. This preeminent textbook concluded that all diets that result in weight loss do so on one basis and one basis only. They reduce total calorie intake. A consensus statement from the Endocrine Society said that the impact of diet on obesity risk is explained largely by its effects on calorie intake, rather than by changes of either energy expenditure or the internal metabolic environment. Stated differently, a calorie is a calorie. And if all calories are alike to the body, then to lose weight, you have to eat fewer of them or move more to burn them off. The Dietary Guidelines for Americans, current edition, says that losing weight requires adults to reduce the number of calories they get from foods and beverages and increase the amount expended through physical activity. The National Heart, Lung, and Blood Institute, on a webpage for balanced food and activity, advises the public to look at the estimated calorie requirement chart that they provide to get a sense of how many calories, energy in, you and your family need on a daily basis. And the most logical expression of this energy balance model was the 1990s low-fat diet. Because fat has twice the calories per gram or per bite of carbohydrate, the thinking was that by reducing all fats, we would naturally be able to maintain weight more easily. And instead, we were told to eat a lot of carbohydrates, all sorts of carbohydrates. If you'll recall, up to 6 to 11 servings a day. Now, this thinking pervaded academic nutrition at the time. These are statements by leading nutrition experts just a quarter century ago in leading nutrition journals. One group wrote that when people are allowed to eat from ranges of high fat or high sugar foods, passive overconsumption only occurs with fat. It follows that fat promotes overconsumption while sugar probably prevents it. A second group said the evidence intriguingly suggests that it is specifically an increased intake of sugars rather than of complex carbohydrates that tends to dilute fat energy. And a third group said by decreasing the dietary ratio of fat to carbohydrate, macronutrient balance may be achieved with less emphasis on carbohydrate source. So these statements are very clear. They're saying that all carbohydrates, including sugar, are good and all fats are bad. And so based on this thinking, the supermarkets filled up with these low-fat products in which fat was removed and sugar and starch were added instead. The fat-free SnackWells, the low-fat Twinkies, even the fat-free Half and Half, if you can imagine that. All of these products have not only less fat, but fewer calories per bite, lower energy density than the original versions. So the thinking was that by consuming these, the population will naturally be protected against obesity. Of course, things didn't work out so well. Calories from fat decreased and calories from carbohydrate as a proportion of our intake increased as expected, but the obesity epidemic took off at its most rapid rate during these last few decades of the 20th century. According to new data from the Non-Communicable Diseases Risk Factor Collaboration, the worldwide, the pandemic of obesity continues to worsen. From 1975 to 2016, there are now 5 times as many adults with obesity and 10 times as many children with obesity. So we have to ask a base question. Why is this simple notion that just eat less and move more, 100, 150 calories less consumed a day, walk 2 or 3 miles more a day, and then over time, virtually all weight problems will be controlled? Why has this paradigm not worked in practice? Well, one possibility is that the energy balance model, as it was originally conceived, focused on the wrong target. Maybe dietary fat isn't the main issue. Maybe the real problem is energy-dense, processed, tasty, or what's called hyper-palatable foods. One review said the problem is attractive, hyper-palatable, cheap, ready-to-consume food products that are characteristically energy-dense and generally obesogenic. That Endocrine Society statement focused on highly palatable and energy-dense diets predisposing to excess weight gain. Now, I think we can all agree that this dietary pattern is not going to be good for most people over the long term. But what's the evidence specifically that it's the energy density, the processing, or even the tastiness of these foods that's the problem, rather than some other component of these foods? One study that aimed to look at this took 20 young adults who were given either unprocessed or ultra-processed diets and for 2 week periods, during which they were allowed to eat as much or as little of these foods on a metabolic ward. So they were inpatients in the hospital during these stays. When the participants received the ultra-processed diet, they consumed about 500 calories a day more than when they consumed the unprocessed diet. But this effect weaned progressively over the 2 weeks. If one simply extrapolates this effect out to 4 weeks, it would virtually vanish, raising the possibility that these are transient responses in the artificial setting of a research ward, not chronic effects. A review on ultra-processed foods said it remains unclear whether associations with obesity can be attributed to processing itself or the nutrient content of ultra-processed foods, and the potential for residual confounding was high. A second review on variety and palatability said, in humans, no studies have systematically manipulated dietary palatability to examine long-term effects on weight. There is a similar lack of epidemiological studies examining associations between exposures to more palatable diets and weight change, meaning that direct effects on weight in humans remain untested. So let's consider these two tasty foods, olive oil or sugary drinks. Most people would consider them both palatable. They're both extensively processed. They're single macronutrient extractions from a plant. In the case of the olive oil, all of the calories come from fat. The sugary beverage, all the calories come from a carbohydrate. The olive oil has massively higher energy density, about 20 times, more than 20 times higher than the sugary beverage. But the sugary beverage is consistently related to excess weight gain, overeating, and other adverse health effects in clinical trials and other high quality studies. Not so the olive oil, quite to the contrary. In the best long-term studies, the people who are consuming more olive oil tend to be thinner and have protection against cardiovascular disease and diabetes. Now let's consider a third food, baked potato chips, also tasty for many people. Baked potato chips are not extensively processed. Potatoes can't be eaten raw, so all baked potato chips are is sliced and baked. Baked potato chips have higher energy density than the sugary beverage, but still much lower than the olive oil. And yet, baked potato chips more closely resemble the sugary beverages in its effects on weight gain and increasing risk for diabetes and heart disease. And I'm not even sure that this notion of palatability would pass the taste test. The US leads the world in rates of obesity. Is this specifically because we have the world's most delicious cuisines? I would think that the Italians, the French, and maybe even the Japanese would debate that possibility. And think about application to practice. If palatability, if tastiness is the main problem, then is the solution to eat a monotonous, bland diet to avoid inexorable weight gain year after year? All right, well, maybe the issue really isn't that it's just energy dense, processed, tasty foods. That the energy balance is inherently a complex notion. This is the UK government's obesity system map, showing hundreds of relationships among diet and physical activity, behaviors, socioeconomic factors, and others. And if you look really carefully at the center, it all converges on energy balance. Now, admittedly, obesity is complicated, but models like this are not useful. They don't guide us to identify actionable factors in the environment or behaviors. And how are doctors supposed to give their patients a map like this and have the patients follow these arrows and figure out how to control their weight? We have a basic puzzle that we have to confront regarding the obesity pandemic. Clearly, genetic factors, biological factors influence individual predisposition for obesity. Some people seem to be able to stay thin these days, regardless of what they eat. Other people are highly susceptible to weight gain. What we have to ask is, what specific environmental factors are causing body mass index to increase year after year, among genetically stable populations. In the 1960s, the average man weighed about 165 pounds. If you force fed him to increase his weight to 195 pounds, he would feel very uncomfortable, overstuffed. His metabolism would speed up to burn off those extra calories. He'd lose all interest in food. And once the force feeding stopped, his weight would tend to come back right down to where it started. Today, the average man weighs 195 pounds in the US. If you starved him to bring his weight down to 165, he would also be miserable, very hungry, his metabolism would slow, and once the food restriction ended, his weight would drift back up to 195 pounds. With its assertion that all calories are alike to the body, the current way of thinking about energy balance implicitly rules out the most plausible environmental factor that could be pushing up our body weight set point, which is the kind of diet we're eating. So there's a third possibility for why this conventional way of thinking has failed, that the relationship between energy balance and weight gain is tautological. In other words, it's telling us what we already know. It's restating a law of physics, and it lacks a focus on biology. Equating positive energy balance with weight gain or fat gain is basically a meaningless statement. I'll go so far as to say it's a colossal waste of effort. Let's consider fever. Would we conceptualize fever as a basic problem of heat balance? Too much heat into the body, not enough heat out? Well, of course, the only way that a person can develop a fever is if their body generates more heat than it dissipates. But this is obvious. This is a fact of physics that hasn't been debated for 150 years. Textbooks on fever don't begin with statements about heat balance. So why this incessant focus on calorie balance when it comes to body weight? To step out of this tautology and to begin to ask about cause and effect, we have to replace these equal signs with arrows, directional arrows, and ask, again, what's cause and effect? Does the positive energy balance cause increased body fat storage? Or does increased body fat storage cause a positive energy balance? Neither possibility conflicts with the law of physics. Let's consider this example, the adolescent growth spurt. During puberty, a teenager might consume hundreds or even 1,000 calories more than he or she used to. But does this relative overeating make the adolescent grow quickly? Or does the rapid growth and the uptake of those calories into new body tissue make the adolescent hungry and drive overeating? Again, neither possibility conflicts with physics, but they have markedly different implications to understanding growth and to the clinical approach to treating growth disorders. Coming back to obesity, the conventional view considers the arrows flow from left to right. Overeating drives weight gain, and thus the focus from this perspective, if the problem really is overeating, is to eat less and move more. But an alternative way of thinking about this, according to the carbohydrate insulin model, is that obesity is a basic metabolic disorder of fat storage. Something has triggered our fat cells to take in and hold on to too many calories. So there are actually too few for the rest of the body, at least at key points after a meal. And the brain recognizes it, and that's why we get hungry. That drives food intake. And also, the brain may suppress energy expenditure trying to conserve calories, thinking that the body is basically in a sort of a starvation mode. From this perspective, the recommendation to eat less and move more is not focused on the cause of the problem. It's focused downstream on an effect. And therefore, it's unlikely to be effective for most people over the long term. So what could be triggering excessive body fat storage? Well, one likely candidate is too much of the hormone insulin. Insulin is the granddaddy of all fat storage hormones. And insulin regulates the availability of all of the fuels that the body uses: glucose, fatty acids, ketones. Insulin stimulates fat synthesis and buildup. Insulin also inhibits release of fatty acids from fat cells and prevents it from being burned. We know that states of increased insulin action go along with weight gain, such as excessive insulin treatment in diabetes, or certain genetic variants in humans that result in increased insulin secretion. These are strongly associated with weight gain. We can say causes weight gain. The opposite's also true. States of low insulin action go along with weight loss. For example, a child with type 1 diabetes, before starting insulin, will have invariably lost weight no matter how much he or she is eating. And it takes insulin to return growth to normal. So if insulin could be triggering fat cells to hoard too many calories, what could be raising insulin? Well, that's nutrition 101, all of the processed carbohydrates that entered our diet during the low-fat years, both the total amount, but also the type is characterized by a term called glycemic index. The basic concept here is that the processed grains, white bread, white rice, potato products, digest very quickly into sugar in the body, rapidly raising glucose and insulin, whereas less processed carbohydrate foods, such as fruits, whole fruits, still, they turn into glucose, but do so much more slowly and result in a lesser increase in insulin levels. A concept called glycemic load is central to the carbohydrate insulin model. It's basically the amount of carbohydrate consumed multiplied by the glycemic index of those carbohydrates. It's the best predictor of how glucose and insulin will actually change after the meal. The take-home point here is that processed grains, potato products, and added sugars are high glycemic load, whereas minimally processed grains, the way that grandma used to serve them, like steel-cut oats rather than instant oats, whole fruits, beans, and the sugars that are present in dairy are low glycemic load. So let's have a look at a few studies of how glycemic load affects metabolism. Now, I'm going to go through these fairly quickly, but the slides will be on the website, Commonwealth Club. And so if you miss any key points, don't worry. You can go back and take a second look. In this study, we looked at 12 adolescents with obesity, and we gave them on 3 separate days diets that varied in glycemic load. One breakfast was highly processed carbohydrate, so instant oatmeal. The second was minimally processed carbohydrate, steel-cut oats, or old-fashioned or Irish oatmeal. These 2 meals had the same amount of carbohydrate, protein, and fat. We also included a vegetable omelet with more fat, a little more protein, and less carbohydrate to see what might happen when we maximized effects. So here's what happens to hormones. This is insulin, which, as we now can expect, rose substantially higher in the first hour or 2 after the instant oatmeal than after the steel-cut oats or the vegetable omelet. So big differences in the amount of insulin that was secreted. At the same time, a second hormone called glucagon was suppressed. Now, glucagon is sort of the yang to insulin's yin. It's the opposite. Whereas insulin promotes storage of calories, glucagon pulls calories out of storage form. Glucagon is suppressed by a high glycemic load meal. So you have too much of a storage hormone and not enough of a retrieval hormone. So that's a metabolic double whammy. And what's going to happen is shown here, that after the initial surge of blood sugar after the meal for the first hour or 2, blood sugar comes down and then reaches a relatively hypoglycemic range several hours after the meal. And free fatty acids. Now if you're going to lose weight, you have to burn free fatty acids that are released from fat cells. But their release from fat cells is also suppressed under the effects of the high insulin and low glucagon. And the brain recognizes this as a problem. The brain triggers a stress hormone or counter-regulatory response. It tells the adrenal glands to release epinephrine, thinking that we're starving and we need to somehow get an emergency access to calories. So epinephrine levels were much higher after the high glycemic load diet than after the other 2, even though the same calories were consumed just a few hours earlier. And the participants in our study got substantially hungrier and ate many hundreds of calories more after the high glycemic load meal than after the other two meals. Well, the key question is, do these effects persist? And to examine that, we first looked in an animal model. And of course, animal models of obesity, they're in many ways easier to do. You can't study humans with all of their factors and exposures controlled for years. You can't lock up people in a metabolic ward for that long. But at the same time, animal studies have to be interpreted cautiously because, of course, humans are not rodents. So I'll just present this results for background information here. In this case, we looked at rats who were given identical diets, differing only in the nature of the starch used: high glycemic index amylopectin, that's quickly digested, or low glycemic index amylose starch. And we further controlled their weight between the two groups to keep their weight the same by controlling food intake. This slide shows body weight in the two groups, average body weight over the 18 weeks of the study. That would be like a few years for a human, given their relative lifespan. I think you'll see that we were successfully able to keep average body weight the same for the two groups. But to do that, we had to start restricting the high glycemic load animals' food intake. Why? Because they began to gain weight excessively, and if we didn't restrict their food intake, they would have begun to deviate by substantially more. So if the animal consumes fewer calories to achieve the same weight, what do we know about it? Well, we know its metabolism is slowing down. That's one of the predictions of the carbohydrate insulin model. So in any event, you'll see at the 18-week point, the weights between the groups were virtually identical. And despite that, the animals had 70% more body fat. And if they were the same weight and they had more body fat, they had less lean tissue. They were also shorter. Now I'm going to show one graphic slide coming up. This is an animal dissection slide, so if that bothers you, please close your eyes for one moment. These two animals weighed the same. In fact, the animal on the right consumed fewer calories, and yet it was massively fatter than the animal on the left. There is no genetic differences between these animals. There's no way to explain this effect through the calorie in, calorie out, all calories are the same energy balance view of obesity. This slide shows that there's something about these diets that's triggering fat storage even when calories are restricted. Okay, anybody who closed their eyes can open them again. We're safe. So now let's go back to humans. There are a number of longer-term dietary trials that compare low-fat to low-carbohydrate, high-fat diets. And opposite to what was believed in the 1980s and 1990s, the low-fat diets, the high-carb, low-fat diets are consistently inferior to the high-fat diets for long-term weight control, according to these meta-analyses, these systematic reviews of all evidence in the literature. Now, the effects aren't big. They're, maybe 2 to 5 pounds difference, but we're going to come back to that issue a little bit later. And I'd like to show you one more study. This looked at, in humans, whether this effect that we saw in rodents, this change of energy expenditure, could also occur. In this study, we took 164 young adults with high body weight, and we first brought their weight down during a run-in period through conventional calorie restriction. If you cut back on calories, for a while, people are going to lose weight. That's just the law of physics. And then we randomized them to either high, moderate, or low carbohydrate diets for a period of 20 weeks or 5 months. During this test phase, we maintained their weight by either increasing or decreasing their food intake to, again, prevent weight change. We provided them with all their meals during this period. It was an epic effort, involving over 100,000 prepared meals to complete this study. And these are the diets. They were either 60, 40, or 20% carbohydrate. And conversely, they had 20, 40, or 60% fat. All the diets had the same 20% protein. This slide just shows this metabolic fuel changes around a meal. The meal was given at time 0, and then we'd followed out blood work for 5 hours. And before the meal, the high carbohydrate diet, there were fewer calories in the blood. And then with the high carbohydrate meal, calories in the blood rapidly increased, but then came down, so that by 3, 4, and 5 hours, there was this crash, this drop off. Fewer calories in the blood, despite the same number of calories being consumed compared to the low carbohydrate diet. So now let's come back to the main finding, which was energy expenditure. We found, using a technique called doubly labeled water, it's a way of measuring energy expenditure among free living people, that those on the high carb diet showed no change in their total energy expenditure. Those on the moderate carb diet increased their energy expenditure by about 100 calories a day. And those on the low carb diet increased their energy expenditure by about 200 calories a day. These were statistically strong effects, and they seem robust. No matter how we looked at the data, we reinterpreted it, we pulled them inside and out, we published multiple analyses, and the effects pretty much come out the same each time. This study suggests that the number of calories you consume, that independent of the number of calories you consume, you could alter the number, this diet suggests that even with, the study suggests that even controlled for calories, you can alter the number of calories you burn just based on the quality of the diet. So let's come back to this big picture of the carbohydrate insulin model. It argues that the processed carbohydrates have increased insulin secretion, and that's stimulated fat cells to take in and hold on to too many calories, so that there were fewer calories available to the rest of the body, to the muscle, to the liver, and to the brain. The brain recognizes that and makes us hungrier. And so we tend to eat more. If we restrict calories on a low-cal diet, it will tend to produce a positive energy balance by reducing energy expenditure. But this model provides a way of thinking about how many other exposures could affect obesity, not mainly by getting us to eat more, but by affecting how fat cells behave, how the number of calories that we consume get either stored in fat or burned in muscle. And these other exposures could include the type of fatty acids we eat, mono, polyunsaturated fats, omega-3s, omega-6s, the type and the amount of protein that we eat, prebiotics, probiotics, the gut microbiome, micronutrients, vitamins, minerals, and phytochemicals. Also, sleep, stress, and physical activity. Physical activity is usually thought of as a way of burning off calories, but by this model, the main effect of physical activity is to alter insulin sensitivity and to reduce chronic inflammation, helping to divert calories away from fat cells and toward the rest of the body. We know that it's hard to interpret the studies of physical activity just based on calorie balance alone, because as people exercise more, they get hungry and they eat more. And so for the most part, physical activity by itself is not an effective approach to weight loss. But perhaps by combining it with this model and with dietary changes that would synergize, we could have a more effective approach. And this model also provides a way of thinking how some of these environmental pollutants, these so-called endocrine disruptors, might be causing obesity and other metabolic problems independently of directly affecting our food intake. Now, I've discussed what might happen on diets with 20 or 40% carbohydrate, which still allows for moderate intakes of fruit, legumes, maybe even a little bit of minimally processed grains. When you get down to very low levels of carbohydrates, say below 5 or 10%, additional mechanisms beyond just insulin and glucagon and those types of hormones are recruited. And that is characterized by ketones. So at very low carbohydrates, these diets are called ketogenic. Ketones are alternative fuels that the brain really likes. Ketones can pass easily into the brain and take the place of glucose. Ketogenic diets are highly effective for certain forms of epilepsy and hold promise for some kinds of neurodegenerative diseases. Studies are looking at the use of ketogenic diets to slow down Alzheimer's disease, for example. So that's a different set of mechanisms that might play a role in very low carbohydrate diets, but this is beyond the focus of our conversation today. So a variety of specific predictions of the carbohydrate insulin model are supported at least by some studies. High fat versus low fat diets result in more weight loss. High glycemic load foods, sugary beverages, refined grains, and potato products top the list for weight gain and chronic disease risk. Reduced metabolic fuels, a drop off of calories, occurs a few hours after eating on high versus low glycemic load meals. Increased body fat accumulation occurs in animals with high versus low glycemic load diets. A point that we didn't have time to go over today, but is supported by a number of studies, that some people are more sensitive to the effects of a high glycemic load diet. People with high insulin secretion, for either for genetic or other reasons, some people, when they consume carbohydrate, secrete a lot more insulin than other people. And those may be the people who gained the most on the low carb, the low fat, high carb diets of the 1990s. In effect, could create a vicious cycle. And then lastly, I showed you a study suggesting calorie independent effects on energy expenditure. The type of calories consumed possibly affecting the number of calories burned. With recent attention to the carbohydrate insulin model in the last few years, there have been a flurry of papers that have come out claiming to have disproven this notion. One paper said the carbohydrate insulin model fails. Another said these data collectively have been taken as evidence of experimental falsification of the model. A third paper said important aspects of the model have been experimentally falsified. I don't have time to go through these arguments in detail, but I believe that they are based on misinterpretations of very weak evidence, including these kinds of arguments. Animal studies that are confounded by unusual combinations of other nutrients. For example, one study created high-fat, low-carb diets, but most of the calories came from either saturated fat or sugar. Saturated fat in rodents, much more so than humans, is highly inflammatory, and it causes very easily documented inflammatory changes in the brain. That's not a fair trial of this hypothesis. It would be like somebody arguing against high carbohydrate diets by feeding animals just sugar. I mean, that would not be considered fair design, and I don't think that advocates of low-fat diets would accept that as reasonable evidence disproving low-fat diets. A second line of argument is these short ward trials that are typically 1 to 2 weeks. Some of them are just 1 or 2 days. It takes the body a few weeks to adapt to changes in nutrients. People who've done ketogenic diets have a name for that. That's called the keto flu. For a few weeks, ketones rise, and people might feel tired. Their metabolism isn't really back up until full speed yet. So looking at these short studies really doesn't give us a good insight into the long-term effects of diet on metabolism or body weight. And lastly, the point I wanted to come back to is these long-term but low-intensity behavioral trials. This is a famous study, the Pounds Law study, published in the New England Journal of Medicine, that gave people diets that varied markedly in macronutrients, either low carb or high carb, low fat, high fat, or low protein, high protein. And the take-home message was that none of the groups, based on their diet groups, showed much of any difference in their body weight after 1 to 2 years. But the problem is that the actual diets that people were consuming really didn't bear much resemblance to what they were intended to consume. The people on the low carb diets really weren't consuming low carb diets. They were for a few months, but by a year, based on the questionnaires, and more importantly, by biomarkers, you can look in the blood or in the urine and see reliable changes that would be expected to take place if people really were eating differently. But for the most part, these biomarkers suggest that there was little, if any, difference between the diets. If you had a study of a new cancer drug, but people in the group that was supposed to take the drug didn't take it as intended. Maybe it was too expensive, or they couldn't find it, or they weren't given proper instructions on how to take it. And people in that group didn't show a benefit in terms of cancer. Well, you wouldn't blame the drug. You'd blame the study. You'd say, we need a better study to help people take the drug, and then we can see if it really works or not. But unfortunately, the vast majority of nutrition research have this poor design. We tell people what to eat. We may have them meet with a nutritionist once every few weeks or every few months, give them recipes, and expect them to do it themselves. That's possible over the short term, but over the long term, in our environment with all of these high carbohydrate, readily available foods, and the basic challenges of maintaining long-term dietary differences, we need something better. Now, there are a few studies that have accomplished this. The DIRECT study was done at a workplace in Israel, where they could give people, they took over the kitchen in the commercial kitchen in the work site, and so that they could give people, based on their dietary assignments, prepared meals that reflected those different diets. Now, people might have not complied very well at breakfast or dinner, but at least one meal a day made for some differences between the groups. And they compared a low fat to a moderate fat Mediterranean or a low carbohydrate diet over 2 years. And here's what they found. The low carbohydrate diet led to rapid weight loss with a little bit of weight gain, so that by 2 years, the low carb and the moderate carb diets were about the same. And the low fat diet was clearly inferior. This difference was about 5 pounds over 2 years. Highly significant, potentially clinically significant. Again, this, we don't know what the maximum effect could be, because compliance at other meals of the day were not perfect. But it suggests that studies are needed to test this hypothesis with much better designs, much stronger interventions that can really support people to maintain long-term behavior change. So as we look forward, we have to keep in mind, in designing research, that obesity for many people that develops in middle age can be explained by the storage of 1 gram of fat extra per day from childhood to age 50, 1 gram a day. That's much too small to see in these short-term studies. So we need feeding studies on metabolic wards where we can control everything, at least a month long. We need behavioral trials with greater intensity, at least a year long. And we need to be able to follow people in their natural lives, collecting very accurate data about what they're eating and what's happening to their metabolism, beginning in childhood, ideally at least 10 years. So we recently published, I did this with 16 other co-authors from around the world, a full model of this carbohydrate insulin hypothesis. We sprung for open access charges so that anybody can access the article and read it for themselves. We state that we don't claim that this is going to be proven correct. In fact, we're confident that not all aspects of the model will be correct, but it offers a clear contrast with the conventional way of thinking by reversing this causal direction, arguing that overeating doesn't drive fat storage, the body getting triggered to store too much fat for a variety of reasons is driving overeating. And we need to rethink the concept of energy balance. So have a look, download the article and see what you think. And lastly, I'd like to conclude by noting that there is already considerable common ground, and that as we continue this line of discussion, people from opposing perspectives, we can generate an even larger common ground and a greater model than either the energy balance or the carbohydrate insulin model. So I've just schematically depicted this in my last slide sequence. Here's the energy balance model, which would typically, although not invariably, tend to encourage higher carbohydrate and lower fat, higher carbohydrate because it's less energy dense. The carbohydrate insulin model, which tends to encourage higher fat. And then a third hypothesis, which I didn't discuss, called protein leverage, which, as the name implies, encourages higher protein. So carb, fat, protein, you've kind of got it all there, except I guess the drinking man's diet from the 1960s, where we could have maybe another loop for alcohol, but we'll leave that aside today. One clear evidence of consensus is sugar. I mean, I think everybody, virtually everybody, with the possible exception of sugary beverage companies, is now identifying sugar as a notably unhealthful aspect of our food supply that seems to be promoting weight gain, more so than just any other food with similar calorie content. According to the energy balance model, sugar is tasty. We have hardwired preferences for sugar, that's, you can see evidence of that in infants. You put a drop of sugary water on their tongue and they kind of smile. If you put something bitter, they grimace. So according to the energy balance view, sugar could be driving food intake. But the carbohydrate model would say, well, all right, once you've consumed that sugar is altering our metabolism in a way that's holding on to those calories and fat cells and further driving food intake. And the protein leverage model would say that, well, the sugar is diluting protein. So we can see that there are actually synergies. Ultimately, we want to know is what kinds of diets are going to be best for whom. And there we can recognize that there are substantial biological variations based on genetics, insulin secretion, earlier life influences, events in the perinatal period. And that might determine for whom a focus more on this energy balance side or this carbohydrate insulin model or this protein leverage might be more effective. But that might change over time. People, as they age, tend to become more insulin resistant. And I believe that maybe this energy balance model would have most relative relevance earlier in life. And that as people get older, well, maybe they need to shift over toward the principles here. But then we can get the broadest perspective, which is recognizing that there are behavioral, cultural, economic, environmental influences that are affecting this whole system, and to generate a model that guides public health and clinical treatment to the most effective approach without getting too attached to which particular model holds the whole story. I think on the, I do want to finish with two final quotes, and to suggest that the ideas that I presented today may be provocative, but they're certainly not new. So here's one quote. The current energy balance theory of obesity, which considers only an imbalance between intake of food and expenditure of energy, is unsatisfactory. An increased appetite with a subsequent imbalance between intake and output of energy is the consequence of abnormal fat tissue, rather than the cause of obesity. Now, this quote comes from 1941 by a visionary physician named Julius Baur. And lastly, this quote, calorie restriction reduces the weight of anyone, obese or lean, regardless of metabolic status, by opposing the homeostatic mechanisms for maintaining energy balance. A more rational form of treatment then would be one which would enable the organism to establish homeostatic equilibrium between calorie intake and expenditure at a normal level of body weight. The use of a diet allowing an ad libitum, just as much as you want, intake of protein and fat, and restricting only carbohydrate appears to meet the qualifications of such a treatment. And this was by Pennington in 1953. On that note, I'll invite you to follow me on social media, and I will.
Well, that was amazing. That was just so much information. Really interesting. And I'm thankful that you did mention that people can to watch these slides again, because they might want to study it. Look at the link is going to be posted, if it's not already, either on the site or sorry, I was looking at some comments from viewers here. So the PowerPoint will be available so people can watch it, as well as to read the original study. So there is one question, or a couple questions that are really dialed down questions. And then the other points are how to make this easier to understand, but we'll do that in just a moment. So here's the more technical of the questions by our viewing audience. There is an opinion that intracellular lipids inhibits insulin action. So low-fat diet advice. Your opinion?
Okay. I believe what the question relates to is something called ectopic fat deposition. So let's step back for a second. What's the purpose of fat cells? Well, they're really important. If you don't have fat cells, you have got a tremendous metabolic problem. It's called lipodystrophy, and people with severe forms of this die of advanced cardiovascular disease very early in life, like in their teens or 20s. What fat cells do is they have to do two things. One is they have to take up calories from a meal when we're eating, because we consume many more calories than we need at that moment. So fat cells, when they're healthy, take up calories, but they have to also be able to release them efficiently when we're not eating. And if you can do that, you're metabolically healthy. If your fat cells can't take up calories efficiently, especially in my view, if you're eating the wrong kinds of diets, and you know what I sort of view as the wrong form of diet, but if your fat cells can't do that job, take up calories effectively, then the calories wind up getting stored elsewhere in tissues that can't manage that influx of calories and that influx of fat efficiently. So so fats winds up getting stored in muscle, and that causes muscle insulin resistance. It also gets stored in the liver, and we know that fatty liver is a tremendous metabolic problem. It's present in the majority of people with obesity, and it's a central component of what we describe as the metabolic syndrome. And so, yes, that is a huge problem. But the answer isn't just to cut back on fat. In fact, fatty liver is more effectively treated with a high-fat diet than with a low-fat diet for a variety of reasons. So it's an interesting and complex question, but it takes us back to a focus, just as the carbohydrate insulin model would argue, on the fat cells. We want to do everything we can to transition fat cells into metabolic health. And once that happens, hunger, metabolic rate wind up taking care of itself without the calorie balance calculations and restrictions.
Okay. I've been asked this question a lot over the years, and somebody is asking it today, and that is about Dr. Dean Ornish and his reversal of heart disease on a very low fat diet, whole grain diet. And they want your opinion on that. And if you would, please also explain how Dr. Ornish's stress reduction component of his diet might very well affect the heart disease. So there's.
Well, I'm not going to try to critique in any substance Dean Ornish's diet. He lives just north of you and above San Francisco.
South of me. Yes, he does.
You may have had him on before. You can have him on again. But I'd like to just point out a couple things. First, the carbohydrate insulin model doesn't argue that all low-fat diets are unhealthy. It focuses on the problems that are prevalent in America today, a population with insulin resistance and metabolic dysfunction, who are then eating a lot of processed carbohydrates and raising their insulin a lot. So if you've got insulin resistance, so that means the cells aren't responding to insulin well, and you keep raising insulin, and then you dump in a lot of processed carbohydrates, you get this vicious cycle. It's like the irresistible force hitting the immobile object, and you get a metabolic meltdown, which ultimately leads to type 2 diabetes. So somebody who's metabolically healthy, lean, physically active, like the Chinese peasants for many years, could eat a lot of white rice, but they were working in the fields 10 hours a day or more. But that's not characteristic of the US population today. And secondly, I'll point out that the Ornish interventions are multifactorial. There are many components. It's not just a low-fat diet. He actually, I believe he focuses on reducing the high glycemic load carbohydrates. So it's not, it's reducing sugar, reducing the processed grains, promoting exercise, reducing smoking, stress management. So in these multi-component programs, especially when there are very small numbers of people, as were in his original studies, it's hard to know. You certainly can't make the argument that the fat reduction produced the benefit. It could have been smoking. I mean, we know that cutting back on smoking is going to be a good thing for your heart too.
Yeah. Okay. Now these aren't in any. I was taking a lot of notes as you were talking, and one of the studies, the DIRECT study, where that was the one in Israel, I believe, where they the Mediterranean, you had the first diet, which was a lower fat or higher fat, and then the Mediterranean calorie restricted, and then the low carb diet. I found those three choices of diets interesting that they chose that. I'm wondering if they did not restrict the calories on the Mediterranean diet. I'm not sure why they would have done that, but then would the low carb diet actually, won that little war? Because the Mediterranean diet is, as we all know, a very healthy diet. I'm just wondering why they calorie restricted it, and how, if they would not have, that would have affected the results of that particular direct study.
Well, even the Mediterranean diet was substantially higher in fat than Americans are currently eating or have been recommended. So the Mediterranean diet was 40% fat. I mean, it is Israel, so they're right on the Mediterranean. You assume that they're going to be interested in that. But the key point is that the low-fat diet was calorie restricted. That's how it's been recommended. The idea is that cutting back on fat naturally helps you cut back calories, and if you add a calorie restriction onto it, well, you've got the best combination. And they compared that with a very low carbohydrate diet that let people eat as much as they wanted. So you'd think, if anything, that's biased against the low carb diet, and instead the low carb diet showed the greatest overall long-term integrated weight loss. And so one can play around with designs, and there are strengths and weaknesses. Sure. No one studies, we as scientists get very attached to our studies. We spend years trying to get them funded. We spend years doing them, and then it might take a year or two to write them up and get them published. And we like to think that it's going to just answer all the questions. Right. But that's almost never the case, especially for a complex problem like obesity. We're going to need multiple different diets, different studies with different designs to come at this in different ways to get a fuller picture. And I think, in our paper on the carbohydrate insulin model, we call for depersonalizing the debate. Social media diet debates are pretty ugly. And sometimes it's unfortunate when scientists engage in that. We need the scientists from all sides to be arguing as strenuously they can about the ideas, but keeping it unpersonal, non-personal, avoiding ad hominem, like they did, in the old British debate societies. You attack the opponent's ideas as vigorously as you can, and then you all go out for a beer afterward. We need to remember that we've got an epidemic of obesity that nobody has solved. This is not an abstract question. Diabetes in the US alone is costing $1 billion with a B, $1 billion a day. Tremendous patient suffering, enormous economic costs. We need to work together to come up with answers that are greater than anybody's vision alone. No one person, no one scientific team is going to solve this.
Well, and, bringing it down to another question, it's like, this is, please summarize for people, dummies like me. I'm sure that's not the case, but anyway, but everybody is a biochemical individual there. And as you say in one of your slides, there are genetic components with this, how prevalent that might be. And we'll get to that in a moment. But one diet, a low fat or a low carb or whatever the diet, it might work very well for you, but it might not work for me, so we have to, and by having the scientists and the powers that be arguing, it's very confusing for the average person not in this world. And it's like, what do I do? What do I eat? So that's kind of a segue a little bit into, what they're doing in Brazil, with their food, how they do the Brazilian food guide. I mean, I would think, it classifies food into 4 categories, the unprocessed fruits, vegetables, processed foods, processed culinary ingredients, processed foods, and then ultra processed foods, which we all can agree is where the big problem is. So, and they've had great success with this. And it seems like for the consumer, having foods categorized somehow, because I think we could agree, if this average person, going back to this person's comment, please basically demystify all this. What the heck do I do? So much information. I would think we could all agree on people should just stay away from ultra processed foods. And
let me jump in there. I think
please do.
There's I think a much more famous and brilliant person than myself once said, we want to make it as simple as possible, but not simpler. Okay. And so remember that it did seem pretty clear that just cutting back on fat is going to be a good thing. It was arguably the biggest public health experiment in human history, was the low-fat diet. It didn't work out well. And my presentation, and I believe that if we could make a similar mistake if we focus on food processing in the wrong way. I showed you examples of highly, stepping aside from that particular system, but I showed you 2 highly processed foods, olive oil and a sugary beverage. They have opposite effects on body weight. So we want to be careful, and we want to make sure that the systems that we generate to guide dialogue and to guide, more importantly, consumer choice, are based on a solid understanding of mechanisms. And I think that's been missing. That's what's needed in nutrition research, to bring the research back to understanding, this causes this and that causes that, and let's test it and let's figure out who's susceptible and who's not. But in terms of practical guidance, I don't think anybody is going to disagree. Many people are going to disagree with the recommendation to reduce processed carbohydrates. So refined grains, many potato products. There might be a little debate about that from the potato manufacturers, but and added sugars. And I think that increasingly people are recognizing that some of these high-fat foods that were stigmatized, nuts and nut butters, olive oil, avocado, even dark chocolate, full-fat yogurt, that these are among the healthiest foods that we can eat now. They're delicious. They're going to help you feel satisfied, and they're also going to reduce chronic disease risk at the same time.
So I've been told that we need to wrap it up. So how about this for the people who need a summary? Eat. Don't be afraid of fat. Eat whole grains when you eat them, maybe on the low carbohydrate side. Watch your one slide, stress reduction, get some exercise, and stay away from sugar. I think that was the center of your Venn diagram.
I tried to come up with a Michael Pollan-esque
Yeah.
ode. And so my version, for the moment, based
Yeah.
on the carbohydrate insulin model, is
Okay.
forget calories,
Mhm.
focus on food quality, and let your body do the rest.
Oh, okay. So for the person who wanted a summary, I think that's the best summary. That's just wonderful. So I think with that, we would all very much like to thank you for being here today, Dr. Ludwig. This was really wonderful information. So we thank you for your comments here today, as well as to all of you listening to this recording and this program. This program and more like it will soon be posted on the club's website, www.commonwealthclub.org. And now, this meeting of the Commonwealth Club of California, commemorating its 118th year of enlightened discussion, is adjourned.